I promised myself I wouldn't start with any corny math jokes about the matrix in this matrix lesson. So let's just swallow the pill, sorry, couldn't help myself, and get started with the lesson. A matrix is an array of numbers surrounded by brackets. An example of a matrix would be the one I circled here in blue. We define matrices by their dimensions, which are the number of rows by the number of columns. For instance, in this matrix, I have 2 rows and 3 columns, so we call this a 2 by 3 matrix. Identifying the dimensions of the matrix is really important when we're dealing with adding, subtracting, multiplying, as you will soon see. When you multiply matrices, there's 2 main processes you could do. You could multiply a matrix by a scalar, or you could multiply a matrix by another matrix. Let's discuss multiplying by a scalar first because it is the more simpler process. When a matrix is multiplied by a number, which we also can call a constant or a scalar, you literally just distribute that number across the brackets and multiply by whatever's on the inside. So for instance, we would take that 2 and we would distribute it to the 4. So 2 times 4 is 8, and put that in the same position that the 4 was originally in. You would repeat the process with the 0. 2 times 0 is 0, and you write that in the place where the 0 originally was. And you continue until everything inside the brackets have been multiplied by the scalar. And that's it. When we are multiplying a matrix by another matrix, the process is a little bit more complicated. First, we have to decide if those 2 matrices can be multiplied together in the first place. In order to multiply one matrix by another, the inner dimensions must match. And what I mean is that the number of columns in the first matrix must equal the number of rows in the second matrix. So if we take a look at this example here, if I have a 2 by 3 matrix and a 3 by 5 matrix, I can multiply the 2 by 3 by the 3 by 5 because the number of columns in the first matrix does equal the number of rows of the second matrix. They're both 3. The resulting matrix, the answer, will be the outer dimensions. So the result will be a 2 by 5. However, if I had a 3 by 5 and I'm trying to multiply that by a 2 by 3, that cannot be done because the number of columns in the first matrix does not equal the number of rows in the second matrix. 5 does not equal 3. However, if I switched the order, let's say I was trying to multiply 2 by 3 by 3 by 5, that would be okay because now the number of columns in the first matches the number of rows in the second. So I say here, and I want you to keep this in mind, the order matters when you're multiplying matrices, which is different than what we're used to seeing with multiplication. Usually when we multiply, order does not matter. 3 times 7 is the same as 7 times 3. But when we're multiplying matrices, the order does matter, as you can see here, because the inner dimensions need to match. As I go through the process of multiplying 2 matrices together, the reason why the inner dimensions need to match will make more sense. Let's look at an example. Here I have a 2 by 3 matrix being multiplied by a 3 by 2. This is possible because the inner dimensions match, and my answer will be a 2 by 2. In order to multiply 2 matrices, you take the dot product. Dot product involves multiplying the matching members. And specifically what you will do is pick up the columns in the second matrix and lay them on top of the rows in the first matrix and multiply the matching members. So let's look at the first step of this example. If I'm looking at the first row in the first matrix, I have 1, 3, and 5. The first column in the second matrix is 7, 8, and 9. Stick your hand out in front of you as if you are going to pinch something in front of you, and actually hover your fingers above the screen so that your pointer finger is right above the highlighted 7 and your thumb is right above the blue highlighted 9. Then what you're going to do is rotate at the wrist, leaving your thumb in place so that your pointer finger turns 90 degrees counterclockwise, and now your pointer finger and thumb are horizontal, left to right. Move your hand and lay your fingers on top of the first row in the first matrix. So now your pointer finger is over top of the 1 and your thumb is over top of the 5. That's what we mean by multiplying matching members. It's essentially taking the first column and rotating it and setting it on top of the first row. Specifically, when you're setting it on top of, you're multiplying the matching members and then adding all of the products together for that sum. So I would do 7 times 1, 8 times 3, 9 times 5. I would get those products, 7, 24, 45, add them together to get 76, and that sum will be in the top left corner where the first row in the first column overlap. It's like in the first row, first column of the resulting 2 by 2 matrix. We will continue the process going through in a systematic way. I like to stick to the same row in the first matrix and then work my way across the columns in the second matrix and then scoot down to the next row. But you can do it however you want to as long as you stay consistent. Again, stick your fingers out in front of you as if you're going to pinch the screen. Put your pointer finger over top of the yellow 10 and your thumb over top of the blue 12. Twist your hand and scooch it over. So now your pointer is on top of the yellow 1 and your thumb is on top of the blue 5. And that'll tell you that 10 matches with 1, 11 matches with 3, and 12 matches with 5. And you can see that we go ahead and multiply each of those matching members, add them together, and write it in the top right corner because that is the first row, second column of the resulting matrix. Now that we've finished everything with the first row, I multiplied it by the first column and the second column. We scooch down to the second row and we repeat. We're going to go ahead and multiply that by the first column and the second column. So pinch that 7 and that 9, twist, lay it on top of the 2 and the 6. So 7 and 2 go together, 4 and 8 go together, 6 and 9 go together. Add those all together and put it in the bottom left corner, which is basically the second row, first column of the resulting matrix. And then we do that with the second column on top of the second row. So pinch that 10 and that 12, twist, lay it on top of the 2 and the 6. You'll see which members match together. Multiply, add, and write it in the bottom right, which is essentially the second row, second column. This is your final answer, your resulting matrix. Let's do an example from beginning to end on our own. Here, I have a 3 by 2 matrix and a 2 by 2 matrix. The inner dimensions match, and I know my result will be a 3 by 2. So I'm going to go ahead and open up some brackets, and I'll fill in the work as we go. I'm going to take the first column and lay it on top of the first row. So negative 2 times 4 is negative 8. Negative 3 times 3 is negative 9. Adding those together is negative 17. I like to do them like this where I get the products, write them, and then the sum. So I know I'm done completely with one thing at a time before I move on to the next matching members. Let's erase these. I'll go on to the second column, sticking with the first row. And because it is first row, second column, in my resulting 3 by 2, it's going to go in the first row, second column. The 1 matches with the 4, and the 3 matches with the negative 1. Adding those together, I get 1. All right, so we're all done with the first row. We're going to repeat that process with the second row. Grab the first column and lay it on top of the second row. Negative 2 matches with negative 2, that's a positive 4. Negative 3 times 5, negative 15. Combining those together, I get negative 11. Moving on. I'm going to stick with the second row, and I'm going to multiply it by the second column. Negative 2 times 1. 5 times negative 1. Add them together. Goes in the second row, second column. Now that I'm done with the second row, I'm going to move on to the third row and do that by the first and then second column. Negative 2 times negative 4. Negative 3 times 6. Add them together. And then we'll move on to the second column. Negative 4 times 1. Negative 1 times 6. Add them together. And that is your final matrix. It does have the dimensions of 3 by 2, just like we predicted, so that's a good indication that we did everything correctly. You could also plug them into your calculator and check and see if you got the same thing. Just remember that the order does matter, so write the first matrix first and then the second matrix. Let's look at another example. Here I have a 2 by 2, and I'm multiplying that by another 2 by 2. This works because the inner dimensions match, and I know my result will be 2 by 2. I like to open up brackets, and we'll do one thing at a time. First row, first column. Even though there's variables, the process is the same. Negative 6 times negative 2, x, is 12x, plus negative 3y times 4y, negative 12y squared. Nothing I can do to simplify that, so I'm just going to rewrite it down here. I guess I can simplify it by getting rid of that plus sign. Now I'm going to do this with the second column. Negative 6 times 0 plus negative 3y times negative 3. Simplifying that by getting rid of the 0. Now that I'm done with the first row, we'll repeat the process, but with the second row. Negative 6x times negative 2x plus negative 2 times 4y. I'll go ahead and bring that down here. And then we do that same process, but now with the second column. Negative 6x times 0, negative 2 times negative 3, and that is your final answer, a 2 by 2 matrix just like we predicted. While these are really fun, there's actually a purpose of these. They are a way of solving systems of equations, as we'll see in this word problem, so that we can make sense of data and numbers in a way that focuses purely on the data without all of the extra terminology. Let's look at this problem for an example. An ice cream stall sells green tea, mocha, and strawberry ice cream. A small size is 75 cents, a medium is 125, and a large is 150. So we have small, medium, and large, 75 cents, 125, and 150. On one day, the number of ice creams sold was the information in this chart below. For instance, the number of small green teas were 10, and the number of medium green teas were 4, and so on. What we're wondering here is which flavor of ice cream brought in the most income and what was the total income. We can use a matrix to do this. Imagine that this information here is another matrix. This first matrix is a 3 by 3, and this matrix is a 3 by 1. I can multiply them because the inner dimensions match, and my result will be a 3 by 1. It also makes sense to lay it out this way because small, medium, large, when I do the pinch and twist, will lay right on top of the small, medium, large information here. So let's go ahead and collect the data. So I'm going to take this column and multiply it by this row. So I have 10 times 0.75, which is 7.5. 4 times 1.25, which is 5. And 6 times 150, which is 9. Adding those all together, I get 21.5. We're going to repeat the process, but now with the second row. 2 times 0.75 is 1.5. 8 times 1.25 is 10. And 9 times 150 is 1350. Adding those together, we get 25. And we're going to do the last stage, multiplying by this final row. 5 times 0.75 is 3.75. 11 times 1.25 is 13.75. And 7 times 150 is 1050. Adding those together, we get 28. What does this mean? Notice how these are arranged is in the same way that these rows are arranged, which means this is the amount of income from the green tea, this is the amount of income from the mocha, and this is the amount of income from the strawberry. We didn't have to focus too much on what we were dealing with. We were able to just look at the numbers by using matrices, and then at the end we were able to make sense of the information. So referring back to the question, which flavor of ice cream brought in the most income? Shocker, strawberry. And what was the total income? We would just add together all of the income brought in by the green tea, the mocha, and the strawberry, and see that the stall on this day brought in a total income of $74.50. So matrices do have a practical use here, besides just so much fun of laying things on top and solving a puzzle and having an excuse to make corny math jokes. Just remember that the dimensions of the matrix is very important, and the order of how you multiply the matrices can really have an effect on not only can the two matrices be multiplied at all, but also what the outcome would be and your ability to check to see that your answer is making sense.